So, yeah, now we're running. Good. Hello. I would like to introduce to talk about the micro drones. In the 60s, 70s, 80s, you know, you could have found those at James Bond. Now you have them in Berlin. And I'm pleased to introduce Mr. Müller and Drouin. And they're going to teach you how to build your own micro drone. Okay, give them a warm thank you. Welcome.
Thanks. So this is how the presentation will go. And you probably all know those UAVs that you can find in the news. They're quite pricey and they're used by the military mainly. So this one is a couple of $1 million expensive. And you also find some civil aircrafts, but still they're kind of pricey. This one is about $1 million. It's used in Japan to spray crop with that. And you also find small aircrafts in the military, but still they're kind of pricey. So this one is about $50,000. And you find stuff that you can use to fly, which is not a real UAV, like this one, which can just let go and fly. And there was just a question why we didn't use quadcopter, but we used fixed wing. I guess this is what most people see as drones if you talk about homemade drones today. We took a little other approach. We have fixed wing aircrafts like these two. We also have some quadrotors, but mainly we're doing fixed wing aircraft, and why we do that, we're going to talk about that later. So if you decide to build your own drone, what do you need? What's the skills? What's the main skills you need to start with the whole thing? The first thing people think about is the aircraft itself. It's an important thing, but you should not put too much effort into the aircraft itself. You should know why an aircraft flies, and you should get a good aircraft, but don't start with a small aircraft. Don't start with a fast aircraft. Take a big, slow-moving, big inertia aircraft that flies very well, and don't start with the small ones right away. You probably have some control loops that you have, which you will use to control the aircraft and the autopilot. You have to push all this information, all these formulas into some computer. You have to have some knowledge in computer software and how you operate that, and you put that into software. Then you have to put this software into the aircraft. You have to have some hardware, some electronics. You probably need some skills on how to operate a GPS receiver, how to integrate antennas, and you probably also have to make sure that the telemetry link or the video link doesn't disturb the GPS, because that's most likely the biggest problem you will have, especially if you have such small aircrafts, that you have a lot of interference between the devices that you have in the aircraft. Finally, you also need RC skills, because the first thing the aircraft will do is it will not work. So you will need some skills to fly it, and even if you're like 500 meters high and flying slow, some strange thing will happen. So you need some RC skills, or even better, you have to know someone that has RC skills who can do the security pilot for you. And that's how we do it all the time. We have one person operating the aircraft on the ground, and we have one security pilot just responsible for the security, and all he will do is look at the aircraft, and if he doesn't like it, he will just switch over to manual and control it. And all this, Paparazzi, we have a lot of team members from various fields. We have people that can build aircraft and people that do electronics. We have skilled RC people on the team. So we're not just from one region, but we try to combine all of them.
My turn? Okay, so when you...
Turn it on?
I'm on?
Okay.
Is it working? Yeah, when you speak about UAV, usually what people will see is the vehicle itself. The vehicle is only a very small part of the system, and if you are going to do autonomous flight, you have to involve a much bigger system. So the first thing you will want to fly the aircraft is what you find on a normal OB aircraft, is a standard RC link. And then comes the big part, which is your ground segment. So you will have a data link, and you will need a data link and a ground control station to see what happens in the aircraft. And yeah, the only problem is not to fly it. Before you fly, you will need to prepare your flight, so define your mission. You will obviously need to be able to do some simulation, because you don't want to rebuild an aircraft every time you made a coding error. You will need to be able to tune your aircraft every time you mount the autopilot on a new aircraft. It will need to be adjusted to this particular aircraft. So plot curves, see how fine-tune the autopilot. Then when you're flying, also the aircraft is autonomous, you will need to monitor what it's doing and maybe interact with him, change some part of the flight plan. And then when you've landed, you will want to be able to analyze the flight logs, because obviously when you're flying, the workload is quite high and you haven't seen everything. So after the flight, you will want to, again, plot some data and see if everything went as you expected.
So the coolest thing about aircraft is that they fly. So we wanted to show you an aircraft in the air, but it's kind of difficult to fly in an urban area like here in Berlin, and we couldn't find a place very close, so that would be kind of impossible. So what we thought about is we set up 3 locations where we have teams right now sitting there in the cold, waiting to start the aircraft. And what we try to do is we want to control the aircrafts flying fully autonomously in Hildesheim and Toulouse from here. So once they are launched, they're flying on their own. We have an aircraft about the size of the bigger red one and another one slightly bigger. And this is something very complicated, even if it doesn't look like, but it took us quite long to set this up. We just set this up for this event. We have never done it before. And so we're going to try to demonstrate that.
Yeah, so before we go with the demonstration, we are going to just give a brief overview of what you are going to see. Then we'll have the flight demonstration, and then we'll come back a little more in depth on what you see. So what you will see is aircraft flying in Hildesheim and in Toulouse, flying their flight plan. So what is a flight plan? Basically, a flight plan will, well, for the most simple, define a trajectory. So the most simple flight plan, you would have 1 or 2 waypoints defining a line, and the aircraft will fly along that line. Now, if you're doing only lines, your aircraft will not fly very well. So you will want slightly more complicated trajectories, like a circle around a waypoint. Once you know how to fly a circle and to fly a line, you'll be able to combine that and fly patterns like this figure of 8. So while our aircraft will fly, we will switch them to that kind of patterns. And with all these basic patterns, you can build a more complex trajectory, like this landing trajectory, where the aircraft will join a specific area, lose altitude, and then fly along what we call a glide and land on the runway. So these are statically defined trajectory, but in a flight plan, this is like a program. You are also, well, in Paparazzi, you are also able to write a flight plan like you write a program and define complex behavior like the one we have here. In this trajectory, the aircraft was fitted with a chemical sensor and is looking for what we call plumes and trying to find the source. So it is starting here. When it finds a plume, it's flying in a cone, making it larger and larger. When you find another plume, it's doing again. And so this kind of behavior is inspired by biological behavior. This is the way insects do. And so this is an example of a complex flight plan. We'll see after that how you can define it.
Right. So this is the ground station that we use. We just go barely over it. You'll see some map on the top. This is from Google Maps. And you see some waypoints, and you see 2 aircrafts, and you see 2 carrots, and the aircrafts try to follow the carrot. And you have a primary flight display where you can see how the aircraft is flying, how it's operating in the air. You have some messages like kill mode. If you switch off the engine, if something strange happens, you probably turn off the engine. And then we have 2 strips over here we're going to talk about later, where you directly can go to special flight plan points and use them.
Of the aircraft.
Yeah. You have like the voltage and the speed and the throttle and every information you need. And what you see in this sheet is that you have 2 aircraft at the same time. That's what we're going to try now. We're not going to switch to Istanbul. We couldn't get a security pilot there. And security is always the biggest concern and whenever we fly. And so we decided not to switch to Istanbul. So we're going to have, hopefully, 2 aircrafts. The mission, or the application in this case, is simply video. So we have a very small video camera, that's the small thing on the bottom, and a very small video transmitter, which you see on the top. And we're going to transmit video from the aircrafts and try to visualize the video, the live video from the aircraft here on the screen.
Yeah, so I guess we are done with a small introductory presentation. And so now we will attempt to fly the aircraft. So we will so this is the same ground station that we showed you before. This is the purple aircraft. This is the aircraft that is in France, and the yellow one is the aircraft that is in design. So you see that the aircraft are in manual for now. Okay. And now we will contact the pilot and let them know that they can switch it to autonomous. So on the map, you see here, this is the map in Toulouse. You see the aircraft here next to the pointer. And it will take off and hopefully go to fly a circle around the standby waypoint. So, can you start with Toulouse? As you want. Yeah, we can do it. I see if they are ready. So they have completed their pre-flight check. I'm waiting for the aircraft to, so I'm switching to the takeoff block. Here you see the video of the aircraft. Okay. Here you see that in this flight plan I have switched to the takeoff block. Now I'm waiting for the security pilot to tell me that he's ready to throw. He will switch the aircraft to autonomous and throw it. So once again, this is something very new and very challenging. You see him walking here on the video, holding the aircraft, so he has realized that I'm waiting for him to take off.
So the pink one is in Toulouse and the yellow one is in Hildesheim.
He's in auto 2. And we are gone. Hopefully. Hopefully we are gone. Yeah, I see that it should give throttle.
So what we have here is a DSL connection. At the home there's a house And even though it doesn't look like, but you can get DSL in France, even if you look that far away from the city. And we have a DSL connection, so we have like 128 kilobits uplink, where we send the telemetry and the video. And in Hildesheim, we have a UMTS phone on the ground, which gives a little less transfer rate, so the picture from there will be worse. And we have a complete system there, so there's a security pilot and there's a laptop, and everything is set up so they can control the aircraft from here. And we just have a sneak entry to the system so that we can see what they are doing, and we can move waypoints or change the flight plan or do whatever we want.
Okay, so the aircraft is now in air. You see it's giving 100% throttle, and it's heading toward the standby circle, where it will hopefully circle. Okay, so now what can we do? Do we want to start the second aircraft now, or
Yeah.
play with this one a little while they get ready?
Yeah, maybe you play with this one a little.
Okay, so you see that it's circling around this waypoint called standby. I will move the waypoint a little. And you see that I changed the trajectory of the aircraft and is now going to fly over the circle. On the video you see my house in the middle of the field. And here you see the aircraft flight parameters, so it's flying 100 meters above ground at an airspeed of 14 meters per second with half throttle, and everything is green, so I have no reason to worry. Now what I can do is I will ask him to go and perform a figure of 8 around the waypoint 1. So the waypoint 1 is here. It's a bit far, but it should be okay. And so we are gone. So you see here the flight plan block changed, and the aircraft is defining a new trajectory. I'm checking that the altitude is correct. Yeah, it's flying. We're losing some of the messages. This is not so common to do that through the network. So
Yeah.
now I can leave it here. You see the video that is transmitted by the aircraft. And what I want to underline is that we only have the security pilot. The security pilot in Toulouse, the only thing he did was to throw the aircraft. For now, we are controlling it from here. And so they are doing nothing in Toulouse. So maybe we will leave this aircraft to fly along this
Figure of 8?
along this figure of 8. This aircraft has an endurance of 30 minutes, so this is perfect for this demonstration. And we will start the second aircraft in Hildesheim. So I will just quickly tell the security pilot that everything is okay, and I'm going to So he told me to go to west because he has the sun in the eyes. Yeah, I moved to west. Ready?
Yeah.
Okay, so we are switching to...
Kill mode. This is not in kill mode. Geh mal auf Takeoff.
You want me to do it?
Yeah.
Maybe.
Immer noch. Okay. Yeah, super. Yeah. Switch over to the other one.
Yeah, that's what I'm trying to do. Ready?
Yeah. Wir starten mal. Oh. Can you switch over to the other one?
Mm-hmm. Okay, so this is the map of Germany. Just while they take off, the map are downloaded online from Google Map. So if you want to fly somewhere, you just need to throw your aircraft, and if you have a network connection, it will download the maps from Google Maps. Oh, and the video, this aircraft has a... No, that's what I'm doing. So this aircraft is transmitting its video through a GSM modem, a cell phone. So this is why it's not refreshing very fast.
Okay. And this aircraft is not tuned very well, so you see the circle is not as accurate as the other one. But it's flying, and you also can see that the data rate is not as good as for the DSL, so we have a little more hiccups in the flight, but still you can see that it is sort of flying. Actually, we have a movable camera in this other aircraft, which you can probably barely see, but you can move this. And unfortunately, we broke this when we tried 2 hours ago, so we cannot demonstrate that. But with this aircraft, you can fly over something and move the camera while you fly over it. So maybe I'm going to demonstrate that next year.
So the problem of link is not very important because, as we said before, the aircraft is autonomous. So if we don't do nothing, it will just fly by itself. And we only need the link to be able to change its flight plan. So I'm reloading the video from the German aircraft, which is on its circle. You want me to...
Yeah, maybe move the circle to stand by a little to the south. There you can see the airfield. These are the cars, this is the hut. They were able to warm a little bit in the hut. And
yeah?
Yep.
So we're waiting for the confirmation.
So what you do now, we send the aircraft the message to move the waypoint, and once we get the acknowledge from the aircraft that the waypoint is moved, the annoying beep stops.
So we changed it. You want me to put it on a figure of 8 or something?
Yeah.
So figure of 8 around waypoint 1. Let's go. So I changed the flight plan block. Yeah. Okay, so this figure of 8 pattern is the one we use when we need to do recognition on a target, because this is the pattern that allows you to fly over a point with different direction and as often as possible. We'll talk after about why we do that. So what else? We could do plenty of things. You see that we have a flight plan with plenty of patterns, but yeah, I don't know how long we want to fly.
Maybe go on with the talk. Maybe go on with the talk.
Yeah.
Okay.
Because I think you've about seen what there is to see. We have an aircraft that flies autonomously. We have video. We are able to act on its flight plan. And yeah, that's about it. So maybe we tell the... So here we go back to Toulouse. You see that the... Oh yes, this was nice. You see that the trajectory are very clean. I'll make what we call a survey. So a survey is a regular survey. Just make sure that the aircraft took the command. Yeah. No, everything is fine. Don't worry. Okay, so you see the point S1 and S2, and the aircraft will be performing a survey in the square between those 2 points. So I will move maybe this point a little here. And crappy network. Okay. He went by to. Maybe the security pilot is playing tricks to me. He went by to standby. I said survey, so I put it back and go see what he says. So, for those who don't speak French, he said I put it back on standby because he was flying south and I didn't understand what he was doing.
Oops. Flying all the way north.
Okay, I'm going back on standby too. Okay, maybe we won't play with the survey today. And I'm going back to standby, so you see he's turning back. So don't worry, flying through network is not something that we usually do, but flying is something that we do very often, and we are quite comfortable with this. So everything is in control. So we go on with the talk and start for the flight.
Will you land? Should I go on?
I tell him.
So maybe I go on. Over. We have some more slides.
So I told him now he can have it and land it. And
So
okay, we'll talk. So now we'll try to explain a little more in details what we demonstrated. So the aircraft that were flying used the software and hardware from a project called Paparazzi. So this project started back in 2003, and on this slide you can see the very first aircraft and the very first electronics. So we are not very proud about that, but it allowed us in something like 3 to 5 months to get an autonomous aircraft. And as Martin said, we used a large, stable, easy-to-fly aircraft, and we used the simplest electronic we could.
in 2004, there was a new hardware developed which contained 2 AVR processors, which had a little more power than the PIC. We had 2 processors. One processor just does the RC, and the other one does the navigation. So if you do fancy stuff in the navigation and the processor crashes, you'll still be able to fly it. So you see these 2 processors. You also see a modem and a power supply.
And we had shrink also the size of the aircraft considerably. The first aircraft was 1.5 kilo. This one was 400 grams. And the first aircraft was 1.5 meter span. And this one is 65 centimeters. In
2005, more teams joined it. We have a team in the US and Arizona. That's the University of Arizona aircraft. And there's a team from Germany joining. So we had more people working on this, taking part in competitions. And in 2006, we had this tiny little aircraft, which is now made by a small company. This is the aircraft you see there.
So this is 30 centimeter span, and as we'll mention later, it's a very big challenge to shrink the size of the aircraft.
And we have a new board designed. It's an ARM7 based board with 60 megahertz, which is a little terrible because the processor is bored most of the time because just navigating is not doing much. So we had to add some applications to get the processor doing something. We also included a GPS on the board, so we had no external GPS anymore, but just this very small board with the power supply and the processor and the GPS all in one board. And it's like 24 grams and more than enough power.
Yeah, this we still had shrink the size. This aircraft weighs a little less than 300 grams.
This one is about 240.
240.
Mm-hmm. So 2007 then was the year where we got into the applications a little more. We did some tests with firefighters. We tried to detect a fire in southern France, so they started a fire. They were a little scared. We thought that they would burn half the forest, but all they did was this tiny little fire, so we were a little disappointed about that. And what we also did, like this year in August, we joined a meteorological survey in Iceland, so we were able to fly in real rough conditions. What you see there in the back is the Hofjellskjol Glacier, and we were doing test flights there to measure humidity, temperature, pressure, and trying to estimate the wind. So 2007 was the application, and also was the year where we brought Paparazzi to people using it. So we teach the meteorologists who fly the aircrafts how to fly them, so that if it works well in March, they will be doing a drive with an icebreaker ship to the North Pole, and they're probably going to use Paparazzi aircraft for that. So, what were the goals when we started all this? First thing was to keep it simple. So if you have the chance to use as few sensors, as few components as possible, you shall do that. So that's what we tried. We tried not to increase the whole system, to have like a bunch of sensors and big computer power. We started small and then increased. So simplicity was a thing. It should be buildable. The whole thing, everything is open source. Everything you just saw flying, all the hardware, all the PCBs, everything is in the CVS. You can just check out and build your own boards and build the whole thing. That also means that we're not using any special parts or something. We're just using electronic components that you can get anywhere. It should be affordable. There's no sense in making 1 million aircrafts. Everybody can do that. So we try to make it as cheap as possible, using expensive stuff only where it's really needed. And we try to be small. Like I said, it's not that big problem to get big aircrafts flying autonomously, but this tiny little thing where you really have to throw it, like you probably have to be American to be able to throw it, to have some baseball training. So this is really small. And this comes due to the fact that the main motor of the whole project was competitions. We took part in a number of competitions to have some points at which you get things done. Like the networking flying we did today, we needed a day to get this done, and this were always the competitions. And for the competitions, we had always the 50 centimeter maximum, so that's why the red one is that size. It's exactly 50 centimeters, or it fills in a 50 centimeter cube.
Okay, my turn. I think we have to accelerate or we'll never make it.
Yeah.
So one of the ways to make something affordable is to use a commercial off-the-shelf product as much as possible. So here you see pictures of many commercial parts that we use in our UAVs. So as Martin said at the beginning, we don't build the aircraft most of the time. By just regular hobby aircraft. We don't build the computers, we don't build the RC links, the data links, we don't build the propulsion, and you can get very good quality stuff for a very low price in consumer shops. Yeah, those slides are here to demonstrate the difference between normal, maybe air-seater is not a good word, maybe RC-OB aircraft and a UAV. So in a RC-OB aircraft, what you have is an airframe, but this is an electric propulsion aircraft. So you have a battery, a radio control receiver, servos, and a motor. And now if you want to turn that into a UAV, what you need to add is what is labeled A, an autopilot, a sensor, what is labeled I, data link, this little purple thing called D, and a payload, because you will be flying for a reason. So usually the payload that is the most widely used is a camera. And now you have a picture of how it looks in real. So you see it's very simple. In fact, since we have developed this little board, everything is on the board. And so basically you only add this board and this sensor, and you have a UAV. This
is the controller board. There are two versions. What when people start the project and they are on the RSC or on the mailing list, they always wanted to start with the big board. That's not what it's good for. I would always start with the tiny, which is on top. This is the board which does have everything in one board. We have the GPS antenna. This is the brown white thing. Then you have the ARM7 processor. You have the power supply and some more parts on the other side. This was the first design we had, which only had 2 processors and nothing else. And in the beginning, we had the 2 processors separated, like I said, for RC and for navigation. And this was what this board was for. And now with the new software, we hope everything goes right and we put everything into one processor. We have sort of separated spaces for the 2 processors, but should be safe.
Okay, I'm going to talk about infrared attitude measurement. So in most UAVs, they will use inertial sensor to tell their attitude. One of the problems with inertial sensor is that they are expensive, at least if you want good one. They are very fragile, very difficult to use. You need to calibrate them properly. And you don't get direct reading from a gyrometer. You get only a rate reading, so you have to integrate that to get your attitude. So you need a fancy filter. This is complicated. We have in Paparazzi, on fixed wing, we use another way to measure attitude, and it consists in thermopiles. So basically, they are just thermometers. Once again, this is consumer electronic stuff. This is used, for example, in cars, air conditioning system. And so how does that work? You put one thermometer on each wing of the aircraft. If the aircraft is level, they will read the same temperature. And as soon as you bank it, they will read different temperature. So we are here talking about radiation temperature. The sky is normally very cold, like minus 40 degrees or something like this, and the Earth is normally warmer. Not always. And so you get an estimation, well, you get a measure of a temperature difference that you have to convert, that you can convert into your attitude, but it's a direct reading. So no need to integrate something, no need to calibrate the sensor. And so how do we get the reading? We add a second pair of vertical sensor, and we just take the ratio of the difference of temperature, and we get a direct reading.
So these are the sensors that we're using. You can find them, for example, in ear thermometers that you have. You put in your ear and you can measure the temperature, and that's done by measuring the infrared radiation of the body that you want to measure. And so you can get them very easily. They might be 10 euros, 5 euros, something like that.
So just something to add, this is not something we invented. This is something that has been used for years and since the 60s, for example, in attitude determination in the satellites.
We have a GPS, which is on the back side, you see here. We also have the power supply, so this is the tiny board from the other side. Unfortunately, you cannot buy this board anywhere. You have to build your own until now, so we are kind of looking for someone wanting to build these boards. And we're doing this for 2 years, I think. We have a data link, various modems on various frequencies. Usually the XP is very nice. It's on 2.4 gigahertz, so if we have video, we cannot use that, so we have some 800 megahertz modems. And we have a two-way communication so that we can set waypoints or change the flight plan.
And this is about all for the hardware. Yeah, just for the modem, there is no perfect modem. You will choose this peripheral according to your mission. If you want to fly far, then you will have a slightly bigger aircraft. You will be able to carry a slightly bigger modem that will need a little more power but give you more range, and etc. Now we'll talk about the software architecture. And so Paparazzi was not designed as a single piece of software, but as a distributed architecture, a small piece of software talking together. So the core of this architecture is a software bus that is called IV, and that allows the application to exchange messages. So this is something that offers functionality similar to what we see in Corba or that kind of thing, but that is much lighter and easier to use. And so here you see the minimal configuration for a ground station, what we have in the laptop here. So you have one process that we call link. This is the hardware gateway. This is where you're going to plug your modem here, and it will make the gateway between the airborne network and the ground segment network. You have this process that is called a server. Well, this is it does almost everything. It's going to log all the messages that are traveling on the bus so that you are able to replay your flight, to analyze it. It will do such thing as sending messages to the third process that we see here, and which is the ground station. So this is only the graphical user interface. So this architecture is very interesting because it's very flexible. For example, if you will be running a simulator, and you will be running a simulator, it will just plug here in the place of link, and this is exactly the same code than the code that is running in the aircraft. We will talk about that later, but we have a good segregation between hardware and non-hardware code, and so we are able to compile the same code for the ARM7 or for the PC, and running the flight controller on the PC exactly as if it was on the aircraft. And this one, Gaia, is an environment simulator which will simulate things like wind and GPS coverage and sort of things. And you can add still more agents. While you are flying, you may want to plot your altitude or whatever, so it's very easy to plug agents such as a plotter, or this one, which can replay a log. So, for example, you could have we could decide to fly, have a real aircraft flying, replay a previous flight at the same time, and have a simulator running. So this is a very flexible architecture that allows a lot of things.
So it's like the Unix, you have a lot of small applications. There's also an application just to show you the raw messages, and you can just plug whatever you want. We also have a plugin for Google Earth, so we can transmit the location and the attitude of the aircraft into Google Earth, and you can see the aircraft fly through Google Earth through this, and it just plugs to the Ivy bus, and that's it.
We have a plugin for flight gear. It's very easy to plug stuff. Yeah, like this, if you have a payload, a special payload in your aircraft, it's very easy to add messages, to write your payload agent. Yeah.
So the onboard software itself is written in C, pretty much. Some of the code that you're compiling, like the flight plan, is directly compiled to C and then linked to the software which is running in the aircraft. And it's all the same C software which is running in the ARM7 or could run on the old RV airboards or also in the x86 or i386 PC simulation. So it's all the same software. It's just compiled differently.
We're just starting to play with ARM9 processors, and it would be exactly the same, and you can bring whatever processor you have as long as you rewrite the hardware layer. You'll fly Paparazzi on it.
The board configuration can be single and twin processors, but like I said, we're not using the twin processors anymore because we're confident that the one processor system can cope with the whole load, and so we're not using it. But we can still use it if we have some real huge aircraft, for example, that we want to make sure that the RC link is still working. We use the two processor boards, and we can still do that with the software.
You can use this feature also not to segregate different critical code, but if you, for example, you have a process that needs a lot of CPU power, you can use this feature to unload the intensive task to another processor. Yeah, and this one is very configuration independent. A lot of the code is generated, and so the Paparazzi will fly small aircraft like this, bigger aircraft with multi-engine, a lot of actuators. It will fly rotorcraft, whatever you want. It's safe code, so we have it's not all written with formal methods, but the critical code has been written using formal method. Real-time analysis, we are in contact with a couple of universities who do that kind of job and who are very happy to test our code for that. And also extensive testing, we have a lot of people flying it, and so the bugs don't last very long, usually. And also it was written with efficiency in mind. It means that the program that you load in your aircraft is not a generic program. We have a compile time approach. Everything that can be tested before flight is static, and this is done using code generation. So a big part of the code that is used for the airborne software is just generated.
This is the flight plan language. I'm probably not going into deep too much. You can write. You can set your waypoints on the top. You can have exceptions, so you can change the flow during the flight. This one is doing something else if it goes above 300 meters. You can do loops inside here. So there's a loop, and you can use math, and you can use any variable you have in the system in flight. So you can do very, very strange flight patterns if you want. You can use the whole Turing complete.
What you find in usually other autopilot is that the flight, they don't have a real language to define their flight plan. Mostly you define a couple of points, or on sophisticated one you can define maybe circles. Here you have a complete language to write your flight plan just as a program. So if you want to write a flight plan that does the complicated thing we showed before to mimic the biologic behavior, you can write that. This is a Turing complete language, and so whatever you can write it in this language. Another big point we've worked a lot for last year is ergonomy. When you fly one aircraft at a time, you can cope with a badly designed graphical user interface. But as soon as you start having several aircraft in the air, the workload increases exponentially, and you really need ergonomic software to help you. So on this picture here, you see that we have 5 aircraft in the air at a time. This is a huge workload on the operator. So this picture shows a screen cap from the ground station from 2003. You see that you see that it's bad. This is a picture from 2005. It has improved a little. And this is a picture from the current ground station. So this is not designed only because it looks cool or because it's practical, but it's designed by people who actually study ergonomy and who study that well. They will come with us, film us while we operate, see what kind of mistake we make that kind of paper mock-up, play scenario on that. You can...
I think we have to hurry a little bit.
Make that kind of mock-up, see how we want to do things, and then in the end, we code the interface that you have seen. You think I should tell more? No. We
this is the interface you had seen. You have a lot of knobs. On the bottom line, you have the flight plan. So there's takeoff. You can see. Then there is a go home. That was the standby circle. So it happens a lot of time that you're flying and something very strange happens, like what we were seeing when the aircraft was going up north. And then the thing you do is you click the home button, and the aircraft will come home and circle over you, and the heartbeat will go down a little bit. You can fly figure of eights, you can fly ovals, and all sort of things. There you have the battery, you have the link status that you probably saw going red a little bit after some time. And we have the explanation here. Obviously. And you see the throttle, you see the speed, and we try to make everything in a way that you have the green color saying it's good, the orange color is like seems okay, and the red color there's really something going wrong, so that with one view you can see if everything is all right.
And none of this is static, of course. It's written in the flight plan language. So if you want to change it, you just write a different flight plan, and you can add buttons, add values.
So it's fully programmable. After the flight, you probably want to find out why the aircraft was flying up north or why it was turning upside down and hitting hard on the ground. And what you can do, you can, all the data that you receive during the flight is logged to your hard disk, so you can look at all the data afterwards, and you can plot that. And here, for example, you can see the blue dot is what the aircraft wanted to do, and the red one is what it actually did, and you can see that it performs very well on this. I'm not sure which one this is, but you can control you can see the loops working or not working, and so you can tune the loops. You have to retune each aircraft you're flying. Each aircraft is a little bit different, so you first fly manual, and then you start tuning all the loops, and you really need a graphical interface to do so.
You do that after the flight, but you can also do it while it flies.
Yeah, you can plot that during the flight. This is some more analysis where you can look in, where you can see an aircraft flying up and down against the wind. And you can see that the turn against the wind was shorter than the turn with the wind. And you can see that the speed increases while it flies with the wind and goes slower after the wind.
Yes, no, we have described the hardware, we have described the software. We will quickly talk about the application. So our primary goal when we started Paparazzi was to take part to MAV competitions. And this is the competitions we took part in the last 4 years, so in fact all of them. And you can see that we performed satisfactory. No, what else do? We don't only do competitions. Competitions are very cool, and this is the main goal. But we also use this for teaching. So as this is free software, many universities use that for teaching different topics around aeronautics. So here is a list of some universities that are working with us.
That we are aware of that they're using it. There are probably more not telling us.
Another application is for research around aeronautics and UAV. You have seen that UAV is a very complex system, and so when you're doing research in a particular topic, you need the system, but you don't want to build it completely. So you can just use Paparazzi and put your little piece in it and do your research easily. So this is a 3D picture from was done in University of Arizona, I think, and those guys study aerodynamics. So they use our Autopilot to study in order to study aerodynamics.
This is a picture taken in Iceland this year, where we were flying with some meteorologists, and they had some other aircrafts here on the floor, and they had this balloon they let go up. And keep this picture in mind, and that's the same picture, just from some further away with Google Earth. And we had a special NOTAM issued by the Icelandic air traffic control, so that we were allowed to fly very, very high. So we were flying up like 12,000 feet, which is about 3,300 meters. And we're not sure, but probably that has never been done with a small aircraft like this. It took us like 6 minutes to go up there, and that's where we lost telemetry, and so we clicked on the come back button because we were not really sure. It's a little strange because you just throw the aircraft, and after like 500, 600 meters, you just shoot nothing, and all you see is the screen, and you're just sitting there and hoping that nothing happens, and the heartbeat goes up with this.
And so you've seen that Paparazzi can be used for collecting data for other type of research. And what we have seen recently also is some operational applications. So this is for detecting fire forest. We have done things about filming waves, finding fishes, and what else? There are plenty of applications. And now we come to the conclusion to leave you a couple of minutes for questions. So what we wanted to say is that the technology is ready. You have seen that this kind of tiny aircraft work, and they work well, they work repetitively. There is a huge field of applications for this kind of vehicles. Every week we see new person coming and say, hey, your aircraft are cool, I want to use it for whatever. A lot of things that are done with real aircraft can be done with small aircraft for a cost that is much less. It has advantage in terms of security also because it's small, it won't hurt people. And this brings us to our third point. The biggest problem we have at the moment is that regulation for allowing us to fly is very behind. It's evolving very slowly. So mostly what we are doing is flying under the radio control regulation, which means that we are not supposed to fly out of sight. Recently, we have seen a case where we were able to fly in segregated airspace. So, for example, this experiment with a fireman, it took place in a controlled airspace, very busy airspace near Bordeaux. And after about 1 year of negotiation, we were able to get an area in this, and we had an air traffic controller on the ground with us, talking with the air traffic control, notifying our takeoff, our landing, and everything, and all this have a smooth integration in civil traffic to allow real operational use. Now we want to acknowledge all the people who helped us to set up these demonstrations. So you seen them here, and all the others that we cannot mention here. Finally, should you want further information, I don't know if we said already, but all this work is free software, so free software, free hardware, free everything, GPL. So this is a place where you can get more information. And now, if you have any questions, you have 2 minutes.
Hello? Yeah, we have only 5 questions because of the time. So,
sorry.
All right.
How much does it cost, a very basic setup?
It costs time. if you're buying the parts for this, let's say 500 euros. If you want if you are making several, it will be cheaper. The cost is your time. It will take you months, maybe years.
How accurate is the attitude measurement with these infrared sensors?
We have no other reference sensor, so we are not able to tell. What we can tell you is that, judging from the result of the competition, where you got a lot of points for the accuracy of the trajectory, we are as accurate, if not more accurate than the other teams, using inertial.
I have another question. On which attitude works this measurement? So works it with low attitude, also with high, or?
Yeah, you can. If you do the math for calculating this, and you calculate that it will still work at 30 kilometers altitude. So it should. Sometimes there's a problem if you're right next to a house or next to a tree, very close to a house or a tree. That causes problems. But altitude, you will not see that in any altitude that you can fly with such an aircraft, where you still have air. If you calculate the horizon, it will not change that much, even at 30 kilometers altitude, and it will still work. We had no problems at all at 3 kilometers altitude.
Thank you.
Okay. What about functional safety? The problem is that normally, if you have such a system, it can cause severe damage. So you have to have three systems that test each other, so that if something fails, the reserve system gets in. And so this thing should be quite dangerous. For example, maybe you fly in an overcrowded area like the Alexanderplatz or somewhere else, or demonstration or something, and this thing hits a person, you get a problem. And so this has to be improved in regarding functional safety.
Yeah. Security is always the most concern. That's why we're not flying on the Alexanderplatz. And you probably saw in the pictures the places that we were flying at were far outside, far away. And we have 2 data links up to the aircraft. We have simulated everything before. Of course, this is not the same as the 30 million Global Hawk aircraft that the US Army uses, and still they crash.
And we are talking about 300 grams aircraft, so even if they fall on your head, you should not be injured a lot. And yeah, given the size of the aircraft, we cannot double or triple every system. So we are doing our best. We're using formal methods. We're using analysis.
But the hardware problems. Short thing. What about regulations? If you do the thing quite short, so that is a very small aircraft, so maybe the air traffic controller won't even notice that because every plane is tested against birds flying into the turbines. So if that thing is not heavier than a bird, it should be no problem for an airplane.
That's what we're trying to suggest to the people who do the regulation. But for now, they don't really believe us.
Okay. Do you think the paparazzi could be a solution to citizen surveillance systems that government could put up?
This is the last question. Thank you.
Well, anyone can use this, and I guess it's used already. Still, I think it's a very bad idea to fly with a fast rotating carbon fiber aircraft over human crowds. So that's nothing that we do, and I would not suggest to do that. So.
And this is not specifically Paparazzi who could threaten, who could pose this problem. This is all kind of UAV. I think Paparazzi problem by giving access to this technology to more people than with commercial material.
Thank you.